or the Parkinson's disease. Alzheimer's and Parkinson's disease are today studied using not human beings or animals. In the first years, you can reproduce artificially your brain using this kind of system. These are the synapses growing between one cell and another. And if you are able to keep the system working the same condition as in the human body, you can study, for example, the action of different drugs, different systems that you can use for testing the validity or not of a procedure without killing rats or small animals or shrimps, etc., etc. At least for 2-3 years, and only the last part of the experimentation, you go to the animals or human beings. But you can reduce killing millions of animals just using this kind of system, which is nothing more than real cell, neural, hepatocyte, etc., in membrane system. It's a very interesting field. Okay, all this talking was for giving you a feeling of why it's interesting to develop more and more education and knowledge in what we call membrane engineering. From neural cell, from medicine, to desalination, to energy production, to raw material production, and many, many industrial operations. Now, for trying to understand and to develop more this field, we have to understand and to study two basic problems: how the operation that we are talking about are working, which are the transport phenomena that are taking place in our membranes, and also how to make membranes. This part of our course is just related to the basic concept of different membrane operation. And we will start from the most traditional one, the most utilized at industrial level, and they are what we call pressure-driven membrane operation. This is the operation in which the system is just a system in which we have a driving force, which is the difference in hydrostatic pressure or pressure across the membrane system itself. You can have other operation where the driving force to the transfer of your species from the feed side to the permeate side can be a delta C, different concentration, can be a difference in temperature, can be a difference in partial vapor pressure, and etc., etc. The most interesting and most utilized class of operation today is the one in which the driving force is just a difference in pressure. Reverse osmosis, ultrafiltration, microfiltration, nanofiltration are typical examples. The same for gas permeation also. So let's start from giving a definition. What is a membrane? This is a very wide definition. You can see here, membrane here is defined as a selective or non-selective barrier that separates and or put in contact two adjacent phases and allows or promotes the exchange of matter, but also of energy and information between the phases in a specific or non-specific manner. That means this is cover basically everything, because normally we are discussing about system in which we are just trying to keep control of mass transfer across the different phases. But in some case, we can have energy transfer, and in perspective, when you're talking about, for example, artificial brain and similar, we are also discussing about transfer of information between different phases. And these are all under the umbrella of membrane science and technology. And that can be in a specific or also non-specific manner. You can see here, you can have a membrane which can be by themselves very selective. That means membranes that have intrinsic property such a way that you have a very specific selectivity. These are membranes in which these are two racemic solution with a level form and a right form, and you can have membranes in which only one of the two forms, the chemistry of these two components is the same, only the space configuration is different. In the case of my hands, these hands are equal, but they are not, they are enantiomeric compounds. They cannot superimpose. They are only just an enantiomeric system. Today, more and more, people are developing, researchers are developing membrane that can be very, very specific in their selectivity. That only the level form can go across, or in some other cases, only the right form is going across. These are systems that we call imprinted membrane system, or some functionalized membrane system. In other case, the membranes has no selectivity at all. When we will discuss about membrane distillation, membrane emulsifier, membrane crystallizers, you are using systems which are just microporous system, hydrophobic or hydrophilic, which no selectivity. The function of these membranes is only to realize a very optimal contact between the two adjacent phases. To realize through this interface what normally is realized in a distillation tower, where you have condensation, evaporation, condensation between different places, you can compact all this in a system which is your membranes. Membrane distillation is exactly this. In this case, no selectivity, but what you have to realize is a very interesting thin layer that can facilitate these contacts between the different phases much better than the other traditional way of doing until now. So these are two extreme cases of membrane operation, membrane itself, very selective, non-selective at all. The other point that you have to consider, today we have many different kind of configuration and morphology in your membranes. You can see the basic structure of membranes. You can have membranes which are porous membranes, or dense membranes, or composite membranes. Dense membranes means a membranes where if there is any pore, is a defect. You will learn in literature, in some case, reverse osmosis, gas separation, people are still fighting and discussing sometimes if the mechanism of transfer of matter across your membranes is related to the pore size, that means sizing effect, eventually at nano level, or other mechanism, the one we will discuss, solubility, diffusivity. No pore. If there is a pore, is a defect. The chemistry, the system is very different. The mechanism will be solubilization of one component in the dense phase and diffusion, the same components in this dense phase. Fick's law will be applied in one case, diffusion, and Henry law will be applied in solubilization. So no pore. In other case, when you're talking about porous, you will discuss about, some case about Poiseuille, viscous flow, convective flow across Knudsen flow, depending from the size of the pore and the size of your particle going across. Very, very two different cases. In some case, the different mechanisms interact or overlaps a little bit, making life more complicated. But you can go from the dense membranes with no pore at all to the very porous symmetric membranes. The membranes can be also symmetric or asymmetric. And that's very important because you will learn that mass transfer across our membranes is very much related to the thickness of the membrane itself. Increasing the thickness for a certain driving force, you are decreasing the flux across your membranes. The overall mass transfer across the membrane is proportional reverse to the thickness. Increasing thickness, less matter is going across. In some cases, not exactly so, depending from which kind of mechanism you will learn that, for example, in some case, you have to increase the thickness to optimize your membrane. This is the case of membrane distillation, for example. But in general, it's vice versa. So the thickness is quite important, so you have to try to realize a very thin layer. The asymmetric membranes or composite membranes has been the solution to the problem. Years ago, people were already aware of the fact that some polymers, cellular acetate, was able to absorb and permeate easily water and not salts. So the idea to have to produce fresh water from seawater by using this material was old, just much earlier than the realization of reverse osmosis. But no one was able to make this kind of idea of interest at industrial level. And the reason was that people were preparing film with the existing technology of the thickness of 100, 200, 300 microns. It was not possible to make thinner than this. And with this level of thickness, also if you apply a delta P of 50, 80 atmosphere, transmembrane flux was very, very negligible, so of no practical interest. One day, somebody was able to realize a membrane where thickness was always 100, 200. But most part of the thickness was material very porous. And only a small thickness on the surface of the order of 1 or 2 microns was very dense. This was the invention of Sid Loeb and Surirajan, who created the opportunity to start with reverse osmosis and to have fluxes across the membranes that were 1 or 2 orders of magnitude lower than before. Because instead of having 200 microns, they had 1 microns. And if you write your equation, that flux was increasing 100, 200, 300 times. And these flux were decent for industrial application. So all this story today that you have to learn in liquid phase, but the same story is in gas phase, to realize asymmetric structure in which you have a material, a film that you can handle in your hands. But this material, most part is porous, and only 1%, 0.1% is dense, and that means it's controlling, is selective, basically. Okay? This can realize in different way, and you can have what we call thin film composite. You can have also 2 different materials form your membranes. You can make in situ polycondensation. You can form a very thin layer, very dense, on a surface of the other material porous. And these are kind of composite material. And this composite can be done by 2 different materials sometimes. You can have PVDF as support and aromatic polyamide as dense film. Or you will learn through methodology that is called phase inversion, thermal phase inversion or phase inversion, NIPS or TIPS will become familiar to you. You will be able to realize this kind of structure not using 2 different materials, but from a single material. You'll be able to have what we call fast, immediate demixing or slow demixing, and changing the velocity of phase inversion, you can realize asymmetric structure as this one or this one. Also here you see here is very large pore, and these here are much more narrow pore. So these things is one material where during phase inversion you can realize this asymmetric structure. So this is just a porous support, and here is the control of the transfer. This one you can have 2 different materials, one on the other, and you can realize by plasma deposition, by polycondensation in situ, this kind of structure. The transport mechanism across your membranes are also different. Depending from the kind of morphology of your material, you can have a system in which what is controlling the mass transfer and the selectivity are just sieving effect. You can have a system which you have a porosity characterized by a certain level. This can be 0.2 microns, can be 1 microns, can be 0.01 microns, etc. And so if in solution you have particles, species which has a pore size lower than the diameter of the pore, they will go across. Water will penetrate. But if you have any solute, a protein or any macromolecules or some species of larger size than the water molecule, for example, they will not go across. They cannot penetrate in the pore, so they will be rejected. And these are just a sieving effect. But you can have another extreme case, totally different. That's the one I was mentioning before. You can have a system totally dense, no pore at all. In this system, the mechanism is called solution diffusion. That means that you can have some species that can be easily dissolved in this phase. That can be, for example, material as celluloacetate, very hydrophilic material in which water molecules can have very high solubility. Other species, salt, for example, or any other chemicals, has no solubility at all, or very, very low in this kind of system. So this species will dissolve initially, and Henry law will control, in principle, in ideal case, dissolubility. And when they are dissolved, now here you are increasing the concentration of this species on the membrane surface, which is much lower on the other side. So you are creating a different concentration of this species between this side of your membranes, of your polymeric phase, for example, and the other side. So you have a concentration gradient, and so this species will diffuse across following traditional law as a fixed law. So you have one thermodynamic phenomena, solubilization. At each temperature there will be a different value of this solubility, and another phenomenon, which is a kinetic phenomena, diffusion. The product of the diffusion coefficient and the solubility coefficient is what we call permeability. When you have this kind of mechanism, permeability is nothing more than the product of solubility and diffusivity. Okay? Both cases are simple, are extreme case, and the real life is always in between. So there is a situation in which these two cases can overlap. Plus, we will also see that now we are talking of materials in which we made no mention about, for example, electrostatic phenomena. We are assuming these materials are neutral material. This is not the case always. We can have materials, polymers, that we are using for making membranes. Are called polyelectrolytes. They have the same properties of normal electrolytes, but in a polymeric form. So they can be materials which has cationic charge or anionic charge, fixed in the structure. You will see that this material can be utilized to produce cationic membranes or anionic membranes, membranes in which what is going through is not controlled by solubility, diffusivity, or just by size phenomena, but is also controlled by what is called dominant phenomena, which means electrostatic phenomena related to the necessity to respect the electroneutrality of the system. And the dominant phenomena, the one controlling most parts of the biological phenomena. All our body is controlled by this kind of phenomena, and some of these membranes are becoming able to transfer only positive ions or only negative ions, depending from the properties of the material themselves, if they are polyelectrolytes with fixed charge positive or polyelectrolytes with fixed charge negative. So this is another kind of phenomenon that will be discussed at the basis of what we call electrodialysis, or the basis of the membranes as the one that you are using in fuel cell, where you can have a very selective transfer only of one species. In fuel cell, for example, the traditional fuel cell we are using today, we have only proton. We are trying to have only proton, H hydrogen plus, going across, not species with negative charge, etc. This because the material has special properties. The naphthalene you are using or the kind of polyelectrolytes you are using are selective only to one charge and not to the other. And this is quite another way of doing. If you have now this material available, you can realize different kind of membrane operation. And that's the one that we will try to describe and to utilize. And they are microfiltration, ultrafiltration, nanofiltration, and reverse osmosis in principle. All of these materials are today standard and in some cases dominant basic unit operation in what we call process engineering. That means in any industrial sector, from sugar production to textile, to electronics, to drug, etc., these kind of operations are much more present than what you expect. Sometimes they don't tell you too much because the public is not yet, does not understand what does it means, and it's easy to have fighting sometimes. In typical case, when you drink milk today, now it's more accepted, but already from few years, you can buy in your supermarket milk cold for with a long time, long life. There's milk, it's called fresh milk, you are supposed to drink in 1 or 2, 3 days. Some other milk can stay longer. Normally, the way to increase lifetime of your milk was to make a thermal treatment. They treat with a very sophisticated thermal treatment, and you destroy most part of the bacteria microorganisms that just create the problem that milk is becoming acid, etc. And that was done for a long time by thermal methods. Still today, in part, with sophisticated thermal methods. Can be done in a very different way. And most part of the long-term milk that you buy today in the shop is no more treated thermally. Because when you treat thermally, you destroy most part of the species of your interest in the milk. Today it's done by microfiltration. Because microfiltration is a system in which you can remove some of the particles, some of the components at the origin of denaturation and the change of the property of your milk, and not the other one. So most part, the milk is going across your membranes with no thermal treatment, so you don't destroy anything, and the species at the origin of the problem are just staying in the retentate. And that is what we call cold microfiltration. When the story started, the people using thermal, they took in court the people producing using membrane, telling what they are doing, this is not legal because there was a big marketing problem, but at the back was the problem that by law, if you read the legislation in Europe that was made 50 years ago, the production of a more stable milk was only mentioned based on thermal treatment. And legally, these guys were right. And there was big fighting famous between Granarolo and Parmalat, two big companies in Europe, and Parmalat lost because they were using new technology not present in the understanding and the legislation written 30, 40 years ago when membranes were not existing. Today, Granarolo, that took in court Parmalat, is using cold microfiltration exactly as Parmalat. And most parts of the world is doing the same. But there are other situations that is still complicated. People don't understand. Most part of the wine that you are drinking sometimes, when they cost more than $5, $6, $10, etc., they are using membranes. Membranes are a little bit more expensive, but you have much better results because you don't change anything in the flavor and the aroma. So when the wine is expensive, you go in Bordeaux, in France, in any cellar where they produce good wine, you will find at the end UF or RO units that is utilized today already in the most famous place for improving the quality of your wine. For example, if they have been raining during the harvesting and there is low sugar content in your grapes, if you want to increase, instead of adding sugar, that is totally different from natural sugar, you can just use a reverse osmosis in which you can eliminate a little bit of water and increase the sugar content, natural sugar content. And that is a normal practice today when it's necessary. But if you tell around that you are using membranes, a lot of people don't understand what are these membranes, and your competitor can tell that no, membranes are polymer, they can release something, and this release can give you a problem. And big stories will take 15 years to show that you are right and there is no release, etc., etc. Anyway, microfiltration, ultrafiltration, nano, and RO are different, not in the strategy, but are different in the property of the membrane you are using and in the result you can obtain. For microfiltration, we are considering a system in which, you can see here, the driving force is a pressure difference of the order between 100, 500 kilopascal, few atmosphere of difference. and the mode of transport is only by size exclusion and convection. What is going through normally is water, small particles, very small as water, or species which are totally dissolved in the solution. What is not going through your membranes is suspended solid, particles of a high molecular weight, colloids and similar. So if you want to clarify and to purify suspension, etc., this is an ideal system. Today, there is much more utilization of microfiltration than, for example, nanofiltration reverse osmosis. Before bottling any beverage, any wine, any orange juice, etc., if you go visiting a company, and when you arrive at the end of the production, before bottling, near the plant where this machine are filling up the different bottles, you will find a microfiltration unit. And you can make a very nice show that, that is microfiltration, I know what it is. Because that is a standard system that at the end of all the production line, eventually the operator don't know, because this system are nice box, and but inside there are membranes that of this kind that just separate the species that can go cloudiness or transformation during the time. And so you have very stable beverage that can stay in a bottle for 3, 4, 5 years. If you don't do this, after a few months, changing the temperature, more light coming in, you will see some cloudiness, the fluid is no more transparent. Ultrafiltration is very similar, but the difference is here, that the pressure difference you can see is the same order of magnitude, roughly a little bit higher eventually. Instead of using 1 or 2 atmosphere, you can go to 5, 6 atmosphere different across your membranes. Same mechanism of transfer, basically the same system. However, in ultrafiltration, you don't have any suspended solids. If you're using suspended solid in ultrafiltration, you can have a problem of plugging, of fouling on the membrane surface, formation of deposit. So you have to pre-treat the solution before entering ultrafiltration. In ultrafiltration, the porosity of your system is, here you have still a membrane porous, but the porosity is much smaller than the one you have in microfiltration. The other difference here is that normally the microfiltration membranes are always symmetric. You don't do asymmetric membranes here. You don't need. The pores are big, and this is a way in which you can realize high flux also when there is suspended solid and similar. In ultrafiltration, you are starting to have asymmetric membranes. That means you have membranes in which the thickness is always 100, 200 microns, but the support is 99% of the very porous, but there is a thickness on the surface much, still not dense, but much less porous. The size of the pore you have much smaller than the one you have on the rest. So these are asymmetric membranes. That is good, because in this way you can minimize fouling inside the pore. Nothing is entering basically in the pore except the species that can go easily across. In this case here, you can have also some fouling inside the pore, and that's what you will learn is quite complicated to clean. So you have to introduce methodology, a little bit sophisticated, to clean the system when something is going inside. It's much easier to clean the surface, because we can anticipate what is making the most clear difference between any filtration system and membrane technology, that we are never working here in dead flow as in normal filtration. In normal filtration, you have a filter, and you just push your membranes on the membrane surface, on the filter surface, something is going through, and the rest you accumulate on the surface, never in the membrane system. In the membrane system, you always have cross flow. That means you are always trying to keep the membrane surface clean with the same level of concentration than in the bulk. And if it does not happen, you are creating what we call concentration polarization, that concentration profile, and that is the origin of problem that you have to try to solve. But in principle, you must always have concentration here and concentration on the surface equal. So you can just predict what is going across your system with no problem from the initial value of the concentration. Not easy to realize this, because there is now, you have to control the concentration profile, but that's what we can try to have. Always cross flow, never dead flow on the membrane surface. When you are going to nanofiltration, the situation starts to change. In nanofiltration, you have a system where you see the pressure difference much, much smaller. You can arrive, much higher. You can arrive, in this case, to 3, 4, 5, 15, 18 atmosphere, from 0.3 to 3 megapascal. And this mechanism is also size exclusion, but you see it's more complicated. You can have size exclusion, the same as here, but you start to have diffusion, the same in RO, and Donan exclusion. So we have 3 different kind of mechanisms that can interact each other and realizing the system. What is going through, by the way, nanofiltration is a very interesting, innovative technology in the last few years. Some of you will be involved in producing nanofiltration membranes, because nanofiltration is a system that is changing a lot of industrial production in good, improving the quality and the performance industrial production in biotech, in the pharmaceutical industry, in the food industry, etc. Because what you can do here is to separate solvents, water as always. By the way, we are always talking about water, but keep in mind that today there is a lot of membrane operation, new membrane operation, new research project in progress, where the solvent is no more water, where you have to produce membranes stable in non-aqueous system. That means in organic solvents, in pharmaceuticals, in biotech, in the petrochemical industry, etc. To make it easier, we are always assuming that water is the solvent, but remember, some of you are working already also here in materials that are stable in THF or in alcohol, in acetone, aldehyde, etc. And that is totally new area of interest that is growing today. We don't have too many membranes doing this work, but people are working on these new materials. In this case, water is going across, some very low molecular species, sodium chloride or monovalent, but the bivalent don't go across. So if you want to separate bivalent, magnesium, calcium, strontium, barium, etc., from potassium, sodium, etc., nanofiltration is doing the job very nicely. That means you can have here selectivity of only 10–20% for sodium chloride that is going through. Magnesium chloride does not go through at all, and that is a lot of necessity at industrial level. So this is one interesting part of the story here, and normally you can have the molecular weight compounds that don't go through. They have a molecular weight higher than about 200 Daltons. So amino acid, dyes in the textile industry, etc., don't go through the membranes, and all the other ones are going across. And finally, the most interesting and important of the pressure-driven membrane operation is reverse osmosis. As you know, reverse osmosis today is what we call dominant technology, much more what people are aware of, and we are, most part of the water you are drinking, of the coffee you are drinking, etc., the tea, is in a way or the other is going through reverse osmosis. Reverse osmosis is a process in which there is no problem of size, no problem, pressure has to be very high, 40, 50, 70 atmosphere, depending the kind of solution, where the mechanism only solubility diffusivity. There's nothing to do with size exclusion at all. If there is any pore here, is a membrane you have to put in the garbage, and what is going across, in this case, is only water. No electrolytes, 99.9%, 99% is the selectivity of these membranes for sodium chloride, for example, potassium chloride, etc. And all the chemical species dissolved or eventually suspended in the solution are not going through, are just what we call retainer species. The retentate is formed from everything except just the solvent water in a good RO membrane. So we can see here, and we have all these membranes available, and you must be able to produce this membrane by yourself. Well, these membranes are becoming more and more popular. I told you last time that when you think a single plant of RO today is installing, the big one, the one that megaton plant, etc., is only about 3 million square meters of these membranes. Huge amount of membranes. Single plant of this size is utilizing 400 tons of the polymer forming the membranes. So this is huge, and the technology it happens only today because technology you will learn is very sophisticated, because you always have to reproduce a system of the thickness of 50 microns, 180 microns, where 1 microns is the surface, the same thickness, otherwise you are changing the fluxes, and with no defects, no pore, no defect, otherwise salts are going across. So doing this, it took about 30, 40 years to be able to produce. But now you have a big company producing this membrane, running day per day, continuously, for supplying the membrane, not sufficient for the request of the market. We have the situation today that big companies are installing new plant in Korea, in Japan, in China, and moving to the Middle East, Toray or Toyobo, etc., to produce more because the people need more membranes, particularly here and here, because this is used in the pre-treatment to reverse osmosis, you will learn. So both this membrane, ultrafiltration and reverse osmosis, we have, the market is asking more than the people are able to produce. And that is quite interesting, and it will be more important in the future. These are the most traditional system, pressure driven, in utilizing for liquid phase. Keep in mind that the same methodology, and sometimes the same kind of membranes, different polymer, different level of selectivity, can be produced with the same methodology, phase inversion, or composite materials, for gas separation. In this department, some of you are involved in big problem which characterize national project, not only water, Siero, but CO2 capture. CO2 capture, hydrogen production, hydrogen purification, CO2 methane separation, etc., are big process running based on a gas separation membranes. Here, gas separation, basically, the mechanism is the same that we have in reverse osmosis. Relatively lower, the same, not too different in terms of a possible pressure difference, only solubility diffusivity. Also here, we must have a polymer in which oxygen can be easily dissolved and nitrogen does not dissolve, or methane, or hydrogen, what it is. If you have this material with this different level of solubility for the different penetrants, you can realize a thin film and applying an appropriate driving force, and one of the species that will be dissolved in the material and will be transferred on the other side. And that's what some of you are doing, and you are studying material which high level of porosity to increase the flux without increasing too much the delta P. And if you are successful in this kind of study, the one that will invent membranes in which CO2 will be much faster and will be easier to be dissolved and going across will solve one of the biggest problems we have today. The warming, the problem of CO2 capture and the storage is one of the major strategic problems. And this department is working on it. Solubility diffusivity, species pass as low molecular weight species, and the other one are the one in which they have lower solubility in the material itself or very slow in diffusivity. That's the one going across. The one that don't go across are vice versa. The one that don't dissolve and don't diffuse, low diffusivity coefficient and low solubility, and eventually has, this is related to molecular weight and so on. Another interesting problem that we will discuss is pervaporation. Pervaporation is very similar in the first approximation to the gas diffusion, but it is different. Here you are looking for materials in which one solvent can be easily dissolved, water, and another one does not dissolve, ethanol. Or you can have some species, some paraform, orthoform of the same hydrocarbons. The paracresol, metacresol, or something similar. And there are species in which the solubility of the two species are different in some polymers. If you do this, you can realize the pervaporation. Again, basically dense membranes, no porosity at all in this case, and the driving force is the different chemical potential or the different concentration of the penetrants, mechanism is solubility diffusivity, and you must have some species that the high permeable species in the polymeric phase and less permeable species or bigger size in this case in the retentate. Keep in mind that from this description there's one point you can focalize. Depending, there are processes here as this one, as microfiltration or also ultrafiltration, where the chemistry of your system is not very important. When you're talking about microfiltration or ultrafiltration, the fact that your membrane is PVDF or is polypropylene or is polyacrylonitrile, etc., is important, but relatively important, because all the mechanism of transfer is just by side exclusion convection. So it's depending from the size, from the morphology of the system, does not depend from the, in first approximation, from the chemistry of the system. But when you are talking about gas separation, per vapor, or reverse osmosis, the chemistry of the system is controlling the overall process. Because in this system, as you remember, we have the mechanism of solubility diffusivity. So here there's a lot of chemistry. The solubility of one component in the polymeric phase is point number one to check. You can do the experiment without some the membranes. You can make in your beaker a piece of polymer and changing the kind of solvent, you will see, and you measure adsorption, desorption, and you will realize if your material is appropriate or not to make a separation, depending not from the morphology of the membranes, as in microfiltration, but depending only from the adsorption, desorption phenomena. So here the chemistry is quite important. Here is quite important, not important at all in first approximation. It's important for the fouling, interfacial phenomena, not for the mass transfer. Theoretically, if you make your simulation and you don't assume any polarization, etc., chemistry does not appear in microfiltration, ultrafiltration. Is essential in here. The interaction between the penetrants and the material is the core of the system. There are other systems, as electrodialysis, where in this case we change the driving force. Driving force here is electrical potential difference. And that's the same in which the mechanism that is controlling the phenomena is 100% Donnen exclusion. We saw Donnen exclusion in part controlling the nanofiltration operation. Here is only Donnen exclusion. Here you have to realize membranes where the parameter we call transport number. If you have any background in electrochemistry, you learn about transport number. Transport number means the amount of current, the quantity of current that is transferred in a system from a specific ions compared to the overall current that is going across the system. In a solution of electrolytes, when you dissolve sodium chloride, you have NH plus and Cl minus. And if you measure the conductivity of this solution, is the addition of the contribution of the sodium and chloride. 50-50 normally, or 48-52, this number. When you have done an electrodialysis, you have a system, cationic or anionic membranes, where the transport number is not 50-50 for the ions. Is 1 for sodium, potassium, so sodium plus, is 0 for chloride minus. That means in these membranes, 100%, 98%, 50% of the current is transported by NH plus and not from chlorine. If it's 1 transport number, is a very effective cationic membrane. If it's 0.5, you put in the garbage because it's not very good. It's the same as in solution. You have to realize this material, this kind of phenomena, using not just normal polymers, but polyelectrolytes. Polymers which fix charge in their structure. Okay? So in this case, you can realize electrolyte, which is becoming very, very important today, because what we call reverse electrodialysis, and we will make some mention on this, is one of the operations in which you can produce energy. Reverse electrodialysis, together with pressure retarded osmosis, is one way to produce what we call blue energy, energy by mixing salty concentration and dilute concentration and taking and transforming the difference in the Gibbs free energy in mechanical work and electricity. Okay, so in perspective, people are more and more looking not only for separation of ions from the solution, but for producing energy based with this kind of membranes. Other old traditional process exists as dialysis, where you have a driving force just different concentration. Only diffusion is controlling here, and that is one of the old way to separate ions or salts from different kind of solution. New processes are becoming now traditional. We will discuss in detail following one by one, but not only pressure driven or voltage driven system exists, but now we have this new membrane operation that we call membrane contactors. And membrane contactors are systems in which membranes is not selective. Here there's no problem with the selectivity of the membranes. The membranes is only optimizing, realizing at the best a contact between liquid phase and gas phase, between two different liquid phase that we want to mix, between one gas and one liquid, etc., just as a contact, so the term is giving. So in this case, the driving force is the chemical potential, or the concentration difference, or the temperature difference, temperature of the membrane distillation, for example. The mode of transport is diffusion. The species that pass are compounds soluble in the extraction solvent, and the volatile, for example. And the one not soluble, the one not volatile, are the one that stay on the retentive side. Membrane distillation is a typical example, following all the kind of membrane crystallizer, membrane emulsifier, etc. Membrane distillation is part of the story, and is mentioned here, where you have a driving force at delta T, only diffusion, volatile are going through, non-volatile don't go through. So if you want to purify fresh seawater and making fresh water from seawater, you can use RO, where you have a very selective membranes in which only water can dissolve and going across, and sodium chloride does not dissolve and will stay back. In membrane distillation, you can have a membranes not dense at all, full of big pore, in which what is happening is creating an ideal contact between the liquid phase and the gas phase, and through the pore, in which only vapor can go, you will evaporate in the pore some molecules, and they will go across with a very small delta T as driving force. And that's totally different from reverse osmosis. For example, in principle here, the selectivity is 100%, because no sodium chloride is going in the vapor phase, so will not go across. When you're talking about selectivity in reverse osmosis, theoretically, you cannot have 100%. Is always a difference in the concentration of some ions across the system. Can be very high, but will never be 100% by definition. So that's what we will discuss in some attention. You can have also membrane-based solvent extraction. In some of these porous membranes, we can entrap some of the complexing agent that people are using traditional extraction by solvents, and that's what we call liquid supported membranes. And these complexing agents, they will operate, they are just down here, they will operate as a carrier. If you are able to control the difference, some parameters in the feed solution and in the permeate solution, here for example different pH, can create a situation in which at a certain pH, the complexing agent that you immobilize in here will interact with one metal, cadmium, and will diffuse across, because now we have difference in cadmium complex concentration, and we release at a different pH. So you have a shuttle that is going from one side to the other one, absorbing one metals and releasing on the other side. These membranes are quite interesting, very selective. The selectivity is related not to the membranes, but to the carrier. But it's a way to operate this carrier in much better way than using big pot of cubic meter of your solvent, of your extractant, at a lot of cost and separation. Here you separate and transfer in the meantime. Quite interesting, but not easy to realize for a long time. To be stable, very easy. Some of these complexing agents can have a leakage in the feed or permeate solution, and so you have some problem if you want to make easy separation, not too expensive. Normally, you can use this methodology for some very expensive drugs, etc., but not large scale. All these processes are basically separations. Membranes can do much more than just separation. Membranes, as in nature, are the first example of intensified system in which you can combine more functions. Membrane reactors are systems in which separation and chemical conversion take place in the same membrane units. You can have a membrane which is catalytic. You can immobilize in the membrane itself a catalyst. So you can have a system in which you can continuously convert and separate if the membrane is selective. Typical example, you can have esterification, hydrogen production, system in which we have very good membranes able to be where we can transfer only water, for example, or only hydrogen, palladium. That means if you make a reactor with the wall in palladium, theoretically, any production of hydrogen during the steam reforming, for example, during the reaction, you form hydrogen, but this hydrogen will not stay in the reaction zone, will move across the membranes and will be continually separated from the reaction zone, which means, if you remember the Le Chatelier principle, or just this basic equation in chemistry, if you continually remove one of the products, any reaction will never reach equilibrium. Any reaction reversible is becoming irreversible. That's benefit number one. But you will see there's a much more benefit than this. You can supply continuously your reactants in the reaction zone. You can remove continuously at the right level. You can distribute in an appropriate way, etc., etc. That's why this is one of the areas of big interest today in process engineering. You can have a full conference around the world only in membrane reactors or catalytic membrane reactors, etc., etc. So we will discuss. And this is another way, another area in which membranes in some cases are becoming dominant technology, particularly in one field, which is the MBR. We will discuss about MBR, I've mentioned already, which are the membrane system combined with traditional biological systems people are using the treatment of wastewater, municipal water. And this one, where one type big biological pond, etc., where everything is happening. Now this is becoming a membrane system, much more compact, very low footprint, much more effective because it is a reactor. So you have to know how to handle it and can be handled. In this country, you have already thousands of small and big membrane reactors, and that's all around the world. So here, in membrane bioreactors are already a dominant technology. In Europe, for us, is BAT, best available technology already very well accepted. In Italy, we have CT living on membrane reactors. Brescia, Prato, if you are familiar with, or some part of Milano, are just, when you are there, most part of the water that you are using, etc., is coming from membrane reactors. In these countries, when you see very big building, etc., in some case, when you go in the cellar, no garage, no wine cellar, but membrane bioreactors where you treat the water coming from floor 35, and in a few hours, this water is up there. They don't tell you too much because you can be afraid of drinking this water, but that is the way in which it's already working. And more, this system will be applied by law, because this is a way to reduce and to reuse as the best of the water. And that is the way in which it is doing. Quite interesting, this system, because big difference with traditional separation system is the fact that theoretically, with the membrane separation system, you can cover all the spectrum of the species to separate that we are familiar with. With the same technology, basically with the same hardware, the same way to realize your unit, which is very important in practical life, you can separate gas, you can separate soluble salt, proteins, virus, bacteria, emulsion colloids, basically going from microfiltration to ultrafiltration to nanofiltration, reverse osmosis. If you want to apply traditional technology and you want to separate this spectrum, you have to change 3-4 different kinds of technology, hardware. You have to go from flocculation to electrocoagulation, to sand filtration, etc. All these things are very different, one from the other. Different background, different basic law. Here, You change the membranes, basically, and if you're not an expert, it's not easy to recognize if this is microfiltration or reverse osmosis. You have to go and reading the pressure that you have been utilizing, or how does it work, because they look similar. And that's, in real life, in practical application, is quite interesting. And so changing the membranes, you can cover all the spectrum of the different components of a solution you have to realize. We will see that the membranes are not realized as as film. You will never see a membranes probably, because the membranes, when you have been producing your membrane, they appear in what we call module. That means they are assembled in a different system and they are prepared in different configuration. Very important, remember when you are preparing your membrane, if you are expert in making hollow fiber, don't try to sell hollow fiber to everybody, because today from the same polymer we can produce membrane in flat sheet or tubular or capillary hollow fiber. But this is not just because we like one configuration, we like the other one. It's because we need, for different kind of separation, hollow fibers or flat sheet. If you are using hollow fibers where it's better to use flat sheet, you are losing 20–30% of your capital investment. You are going to destroy the system. Vice versa, if you are using flat sheet, hollow fiber, when it was possible to use flat sheet, you are losing a lot of money because normally hollow fiber has a cost 5 times higher than the flat sheet. The utilization of flat sheet or hollow fibers does not depend from the quality of your materials. You can make hollow fibers in PVDF and flat sheet in PVDF, or the same for aromatic polyamide, etc. It depends totally from the engineering of the system, for the problem of fouling, from the problem of the efficiency on the transmembrane flux, etc. So nothing to do, in principle, with the chemistry, a lot to do with the engineering of the system. So if you are producing flat sheet, you have to sell flat sheet where the flat sheet are the most convenient configuration. If you are producing hollow fibers, you have to try to sell hollow fibers where hollow fiber can be utilized. Very often, this is not what happens. If you produce hollow fiber, you try to convince the customer that these membranes are the best. And you're losing money, and the customer is becoming nervous at the end. Now this problem in part has been solved because people are becoming more expert. Years ago, it was terrible. People were realizing using hollow fiber because they say there's much more surface, etc., in a compact system, you save. And they destroyed the operation because fouling, biofouling, and big pressure drop across the system, etc. So these are the different kind of configuration existing. Each one has some specific properties which are convenient for specific separation. Flat sheet means that you are just producing a normal film. Very unusual to use flat sheet membranes in real industrial application because you need to have a support if you apply a different in pressure, etc. That costs you a lot. Keep in mind that when you have a spiral, the same flat sheet, if you combine a spiral module, one time they were 4-inch, 8-inch, now they are becoming, here in Korea, you are producing huge module, 36-inch, 27, etc. That means here in a spiral wound module of a 4-inch, that means something this diameter 80 centimeters, there are about 7 square meters of membranes. Now you can make module here where instead of 7 square meters, you can have 300 square meters. You can have 500 square meters, single module. That means the system is becoming more and more compact, you save a lot of material, etc. If you are using hollow fiber from the same material, in here you don't have 7 square meters. In the same side, you can have 500 square meters, 1,000 square meters. Hollow fiber can be my-hairs. Today there are machine here where you can spin system as my-hair. That means 60 microns, 70 microns, hole inside. And the solution is going inside and something's permeate. That is gas phase or also liquid phase. In this case, huge membrane surface is available, and if you control correctly the flow dynamic, this can be quite interesting. But for using this, you must be sure that you don't plug the system. There is pre-treatment to be very effective. The chemicals has to be not polluting, not absorbing on the surface, etc., etc. So it's not, and if you are using this one when it's possible, it's okay. If you use this one when it's not possible, shortly, after a few months or you destroy the system, you have to start again. So you can have a flat sheet in spiral wound configuration. You can have tubular. In some cases, they are 1 inch, half inch, and that's they are used, for example, in the concentration of tomato juice, orange juice, etc. Concentrate very often using tubular membranes. Company in Japan famous on Nitto Denko. They are producing this nice tube. This is very high footprint. That means this for one module, so 2 square meters of membrane is 10 modules of 2 meters long. So it's a lot of, but in some cases unnecessary if you want to have very concentrate solution, very viscous solution. And you can have capillary. Capillary means our spaghetti, exactly the same size, or hollow fiber. So this one can be half of the cent of millimeter or a quarter of a millimeter. This one are just 10 millimeter. And this can be very nicely assembled in what we call that. At the end, what you see here, this is the kind of module where there are flat sheet rolled in the appropriate way. And here to build up this one, still people are making research here. How to optimize the spacers. This is not only membrane. There is a spacer, there is a support, and all the flow dynamic of the system is still part of the research that you have to do to still realize system with a very low pressure drops between the entrance and the exit, etc., etc. But quite interesting. Or you can have the capillary, or you can have this one assembled in this kind of module. So these are the different configurations you will see. Just to show you some of the different that you have to between different situations, when you have a tubular, plate and frame, spiral wound, capillary, hollow fiber, if you are looking to the cleaning, for example, you see tubular is very easy. In a tubular membrane, you can also clean mechanically. At one point of the story, you start to move in the tube some very soft ball, plastic ball or foam ball, and they go across the system and they remove everything from the surface. Any tomato left, any orange left, any rubber left, etc. But if you want to do the same for hollow fibers, forget. No way. That, so the cleaning here is very complicated. Big company as DuPont company that initially started to produce hollow fiber for desalination, they went out of the market. Initially, they were selling a lot of this hollow fiber. Today, Toyobo is the only one in the world still doing, because using hollow fibers, you have to pre-treat very, very significantly all the solution, because there is always something going in and plugging in front. With time, you're just making a deposit in front or inside. So there's big mistake to use the wrong fibers for doing something where the cleaning is complicated. So tubular are very good in cleaning, but very bad in in cleaning, but very bad for example in packing density. Tubular membrane, I told you, for having 3-4 square meters, you have to use 10 meters of footprint. If you do the same with this hollow fiber, the packing density is very high. This is the best way to realize the packing density of our lungs, which are the same problem. Here we have about, between this one and this one, in terms of packing density, is a factor of 5,000. You can realize the packing density, that means the ratio between membrane surface and volume, 5,000 here and here 1, if you want to make a ratio. And the other one are in between, obviously. The same fouling tendency, very low in tubular, and that means cleaning is easy, and very high in the hollow fiber, etc., etc. So it means when you produce in one form or the other, don't try to defend your membranes when you cannot defend them, because the motivation for doing fibers or flat sheet has nothing to do with polymer, has nothing to do with selectivity of permeability, has to do with the engineering, with the configuration of the system where you are going to work. We will start to discuss now which are the fluxes and the driving force that characterize my separation. And that can be the last slide for today. We can have two different kinds of mass transfer across our membranes under appropriate driving force that we saw before. And this is the case in which where we have what we call a passive membrane transport, and the other case in which we have a facilitated transport across. Passive membrane transport is typical case that we will discuss, where we have the membrane that acts as a barrier, which restricts the flux of the various components. Here a little bit more simple than the previous general description, due to their chemical nature, size, or the electrical charge in general. And that is typical, that's in reverse osmosis, in gas separation, etc., etc. And that's the configuration. We have a certain concentration of one component in our feed solution, and we will have a different concentration across our membranes in concentration gradient here, and we will have some of the species going across, and the difference in concentration of the species A in the feed solution and the permeate will be different. That means higher concentration here, and if the membrane is doing the job, much, much lower here. And we have to define what we call rejection coefficient that is characterizing this kind of behavior under an appropriate driving force, and the flux will be in direction of this gradient. You can have other system in which there is not the membrane itself is playing a role, which is not playing here. Here is just a phase. You can have a system in which you can have some carrier block inside the membranes, or some other situation in which we have a carrier mobile in the membrane. This typical case of the liquid supported membranes I was telling before. A system in which you have a complexing agent, quite effective, in blocking one of the metals present in the solution at a certain temperature, at a certain pH. So when this, you can find a way to block this carrier in the membrane structure. Can be done relatively easily. For example, if you have a material here, hydrophobic, you can dissolve in here a solvent as some kerosene, some organic components, in which this complexing agent can be easily dissolved. But this is not dissolving in water. So if you prepare this membrane with your complexing agent dissolving kerosene, the kerosene will not move across, will not go. The partition coefficient is very high, so will not go in the aqueous phase. But at the interface of the kerosene plus complexing agent and water, you can interact and you can block some of the metals that are present in the solution. Now you have been creating a different concentration, so this one will move on the other side. Here is different pH, and you will release. So this is a shuttle going up and down, taking one metal and moving on the other side. This mobile carrier, this one you can have the same by fixed place in which you can absorb one component present here. The same is happening in electrolytic, when hydrogen ions are moving in electrolytic solution, for example. So you can have that, you can jump from one of the fixed place on the vacancy or any defect which is present, and moving across much faster, the component can interact with this position. So that's a fixed carrier membrane. In this case, as you can see, driving force will be the same direction, component only of the component that can interact with this fixed position in the system. And that is the situation that we can have in different kind of membrane, for example, in perovskite membrane that people are using today for the separation of hydrogen or oxygen, or in other kind of materials that people are studying today. So these are some of the different situations. And now we have to see which one are the equation and how these different fluxes can take place. Just to mention here, so we'll not repeat next time, that sometimes the systems are not so easy to understand and to describe, because you can have a situation in which different fluxes can take place in your system, and some of these fluxes interact one with the others. For a long time, people have been talking about active transport across membranes, telling that some membranes violate the second law of thermodynamics. Not true at all. The people were not understanding the overall system they had in front, because if they were looking to the overall system, there was no violation of the thermodynamics. There's cases in which apparently you are moving against concentration gradients, for example, in some of these liquid supported membranes. The problem is that when you are moving against the concentration gradient, if you look all the system, you will realize there is something going the other direction. There is difference in hydrogen ion concentration, with more pH different that you don't realize sometimes, are the one that apparently create a system which you violate second law. We don't violate, everything is correct, but when you have a nice idea of all the overall system, it is okay. Apparently, however, you can have a situation in which you can have an ion go in one direction coupled with the flux of the cation, or vice versa. You can have cation go in one direction and cation is going also in the other direction. When this complicated situation takes place, is only because you have to keep mass balance, but also charge balance. Electron neutrality be always respected, and this coupling of different flux, co-current or counter-current coupled flux, are at the origin of this more complicated. And you can realize hundreds of these different kind of configuration, depending what you want to realize. Okay, we stop here, and we will meet next week. Thank you.